Hi, hello everyone. So this is the video where we deal with section 2.3, polynomial functions and their graphs. I divided this topic into three videos. This is the first one where we go over the definition and the end behavior. Okay, so to begin, when we talk about a polynomial, as you can see here, the definition of polynomial function, the polynomial is nothing more than an expression where we either add, subtract, or multiply multiple terms. So this is one term of the polynomial, this is another, and so on and so forth until the very end. Now, what's important about a polynomial is that the polynomial has sum or subtractions of all of these terms, and each term has three pieces. It has a coefficient, it has a variable, and it has an exponent. Okay? This could be any number, positive, negative, zero, real, integer, fraction. The variable is just a variable, usually x, and the exponent has to be an integer value that is either zero or positive. Okay? No negative values are allowed or fractional values. Normally, we write the polynomial in decreasing order of exponents. So the first term has the highest exponent, and then it decreases all the way to x to the 0. X to the 0 is 1, so we just normally write a sub 0. Okay, so coefficient, variable, and exponent, and the exponent has to be a value that is either 0 or positive. We normally call the first term, as you can see here, of the polynomial, since we write it in decreasing order of exponents, the first term is what we call the leading term. This is the most important term. This is the leading term. The coefficient of the leading term is obviously called the leading coefficient. And as you'll see shortly, to analyze a polynomial, all that we really have to do is find out what the leading term is, the term with the highest exponent, and we just ignore all of the remaining values for the end behavior. So this is what a polynomial looks like. This is the way we write it. And it's just a sum or subtraction of terms where each term may have a coefficient and it's going to have an exponent attached to the variable. Now, here's a couple of examples of two functions that are polynomials and two that are not. Okay, so f and g are polynomial functions. Um, they are listed in decreasing order of exponents, x to the 5, x squared, and then x to the 0. Okay, all of the exponents are legitimate. The coefficients could be any value, integer, right? Irrational or just another integer. And in the first case, because the highest exponent is 5, the degree of this polynomial is 5. In the second case, this is an important case because the polynomial is given to us as a product, which is also allowed. We can write the polynomial as a product. All we have to do is expand and multiply these terms so we know the individual terms of the polynomial. And once we FOIL the x minus 2x plus 3 and we multiply by minus 3x to the fourth, we get minus 3x to the 6 and these two other terms. So the leading term is obviously the one with the highest exponent. This is the leading term, and the degree of this polynomial is 6. All of the other two values are legitimate values. And then we say that this polynomial is a true polynomial, is legitimate, according to the definition. Now, capital F and capital G are not polynomial functions. Now, let's see why. okay? In the very first case, I see radical x. Well, radical x, if I converted the radical form to exponential form, I get x to the 1/2. The exponent 1/2 is not allowed because the exponent must be a integer that is either 0 or positive. This is not it, right? Has to be an integer value. This is a rational value. So capital F of x is not a polynomial. And the same thing goes for the second function, capital G. I have minus 3 over x squared. Well, if I turn the denominator into numerator in exponential form, I get x to the minus 2, which is not allowed because exponents must be 0 or greater than 0, but only integers. Right? So this is not allowed. I don't even have to check the other terms, even if they are legitimate. If there is one term that violates this definition right here, we don't consider it a polynomial. So here's the definition again of a polynomial, right? It's a sum or subtraction of terms where each term has a coefficient, even if it's one, has a variable, and it has an exponent that is either 0 or greater than 0, but only integers. Okay, so we know what a definition of a polynomial is. You saw some examples. Let's take a look at what it looks like when we graph them. And we'll have to graph polynomials in this course. So one of the reasons that we like polynomials is that when we graph them, the graphs look like smooth and continuous curves. Okay, so these two characteristics are applies specifically to polynomials. And when we say smooth, we mean that the graphs have only rounded curves and no sharp edges or corners. And when we say continuous, we mean that the graph has no breaks and no holes in between. Right? Sometimes there's going to be a break for rational functions. We'll see later in the course. But for now, no breaks and no holes for polynomial functions. So on the left, I have two examples of polynomial functions. And in this case, they both will go to infinity, positive infinity and negative infinity, which is not a concern at the moment. The only concern is here is a rounded corner. Here's another rounded corner. So these are polynomials, but something that did something like this, like a sharp edge, would not be a polynomial. Same thing here, rounded corner, rounded corner, rounded corner. These are all smooth, curved, and continuous. Whereas I have these two graphs on the right, where these are not example of polynomial functions because in this first case, there is a break, right? The left piece of the graph is not connected to the right piece of the graph. So this is like a hole. This will not be considered a polynomial. Same applies for sharp corners. These are all sharp corners and do not classify as polynomial functions. Okay? We won't have to graph these functions right now. The ones on the left are rational functions or other types of functions that we'll see later in the course. For now, we're only interested in these ones on the left that are polynomial functions. Okay, so and we'll graph these polynomial functions in the third part of the video. Okay. Now, the other thing that we need to know, now that we know what a polynomial definition is, what the graphs look like, is what we call the end behavior of a polynomial. All right. So let me just make sure I fit this in the screen. Okay, so the end behavior of polynomial refers to where the polynomial is going as it approaches either positive infinity going to the right or minus infinity going to the left. Okay, so you see here on the graph, there are four possibilities for that to happen. Okay, and the way that we determine that is just by looking at the leading term of the polynomial. So if you take a look here again at the definition, as I said before, that we normally write the polynomial in decreasing order of exponents. So the very first term should be the one that has the highest exponent or is the leading term, right? So to determine the end behavior of a polynomial, all I have to do is look at the leading term. I completely ignore the other terms because as x approaches positive or negative infinity, uh, the polynomial is going to be determined by the leading term because it has the highest exponent. The others will become negligible. So there are four possibilities. The leading coefficient test is going to have us look only at the leading term of the polynomial and then determine the end behavior. So I have four possible scenarios. These are the four right here. Now, it looks like the textbook has a complicated way to determine, which is which, but I will show you a very easy way to determine that. Now, let me show you. I have a summary here, what happens as x goes to either positive or negative infinity, but it's pretty simple, you see. Let me show you this case first. Now, look at the arrows where the arrows are pointed, right? This is the end behavior of the polynomial, where each side, as it goes to positive infinity or negative infinity, where does the polynomial go? Does it go up? Does it go down? So in this case, as I am going to the right side of the polynomial keeps going up and up and up. So this thing goes to positive infinity. As the polynomial goes to the left to negative infinity, its left side of the polynomial keeps going up. So it's also going to go to positive infinity. Now look at the second case. As the polynomial as x goes to positive infinity, it goes down. So as x increases, the polynomial decreases to negative infinity. And the same thing goes right here. As x goes to negative infinity, the polynomial goes to negative infinity as well because the arrow is pointing down. Now look at the next case. Let's do this one next. As x goes to positive infinity, the polynomial goes up without bound, so positive infinity. And as x goes to negative infinity, the polynomial goes down to negative infinity. And the last case is exactly the opposite of case number 3. As x goes to positive infinity, the polynomial here goes to negative infinity. And as x goes to negative infinity, the polynomial goes to positive infinity. And this seems maybe a little confusing. Oh my God, do I have to memorize all of these things? And I will tell you, no, it's not necessary to do so. And I'll give you a very nice technique to do this without having to memorize any of these things. This is one way to look at it, and I will give you a better way. So let's take a look at some examples where we are going to find the end behavior of the polynomial. So I have here four examples for us. These three examples is one way in which the polynomial may be stated, where each term is already individual, in an individual format. Now, the last case, it's important because sometimes a polynomial may be given to you in product form. This is within the realm of definitions of a polynomial, right? where the operations can only be addition, subtraction, or multiplication. So we'll take a look at that last. When the polynomial is given in the form of A, B, or C, where each term is already in its individual form, all I have to do is I have to identify the leading term. Okay? So the leading term is the term with the highest exponent. Okay? And then I will do the following. We'll just look at the leading term, and I need to know as x goes to infinity, positive, and as x goes to negative infinity or infinity negative, what happens to f of x? This is what you need to know. So, and this is what you will do to find out. For the positive infinity, you're going to replace x with positive 1. Okay? And then you're going to evaluate this thing. Well, this is 5. 1 to the third power is just 1. 5 times 1 is 5. If this answer is positive, the polynomial goes to positive infinity. All right? If it is negative, it would go to negative infinity. For the case of negative infinity, you're going to replace x with minus 1. And then you're going to evaluate this. So minus 1 to the negative third, I'm sorry, minus 1 to the third power is just minus 1. And this is minus 5. So if the answer is negative, we really don't care about the actual value. We just care about the positive or negative. If the answer is negative, that means that the polynomial goes to negative infinity. So the end behavior of the first polynomial is as x goes to positive infinity, f of x goes to positive infinity. As x goes to negative infinity, f of x goes to negative infinity. All right, so this is the first end behavior. Let's take a look at the second one. So again, we identify the leading term. And then we do the same thing as x goes to positive infinity. It's also important that you understand the notation that we're using. It's part of the course, how to express, the behavior of the variable, which is what I just wrote right here. X goes to positive infinity. And then the end behavior of the function itself. So as x goes to positive infinity, I need to evaluate what f of x is. And to do that, on the positive side, I just replace x with positive 1. And then I evaluate this expression. So 1 to the third power again is just 1. And minus 2 times 1 is minus 2. So f of x goes to negative infinity, right? Remember, we're only interested in the sign. In this sign. This is either going to be positive or negative. It's never going to be 0. Okay? Let's do the other one. As x goes to negative infinity, f of x equals. I am going to replace this now with negative 1, right? Negative infinity, negative 1. So negative 2, negative 1 to the third power. And then I evaluate negative 2 times negative 1 to the third power. So negative 1 to the third power is just negative 1. And negative 2 times negative 1 is positive 2. So because the answer is positive, that means that the polynomial goes to positive infinity. Notice that is the opposite, right? So my answer is, as x goes to positive infinity, f of x goes to negative infinity. As x goes to negative infinity, f of x goes to positive infinity. Next case, same thing. We identify the leading term. As x goes to positive infinity, I am going to replace x with positive 1. And then I'm going to evaluate this expression. So 1 to the fourth is just 1, which means since the answer is positive, that f of x goes to positive infinity. And for the negative case, I am now going to replace x with negative 1. So negative 1 to the fourth is still positive 1. So this is also 3, which means that the polynomial also goes to positive infinity on the negative side. So as x goes to positive infinity, f of x goes to positive infinity. As x goes to negative infinity, f of x goes to positive infinity. In the last case, this is an important case because the polynomial is not given to you in individual terms. It's given you as in product form. Now, remember, for the leading coefficient test, I'm only interested in the leading term. So you don't have to FOIL all of this. All I need to do is find the leading term. Now, the leading term is going to be this number minus 9 times the 2x square and the x cubed. And then I'm going to multiply that. So that's minus 9. And that is 4x squared. And then this is x cubed. So minus 36 x to the fifth. I don't really care about the other terms. If you wanted to, you could multiply everything to find out exactly what the polynomial is. But since I'm only doing end behavior, I only am interested in the leading term. So this is my leading term, and I'm going to do the exact same thing as I did before. So minus 36 x to the fifth. As x goes to positive infinity, I am find the end behavior of f of x. I'm going to replace x with 1. And this is obviously 1 to the fifth is 1 minus 36. So f of x goes to negative infinity, right? Because of this minus. And same thing on the negative side. But now I am going to replace x with minus 1. So minus 1 to the fifth is minus 1 times minus 36 is positive 36. So f of x goes to positive infinity. Okay? So I have the end behavior as x goes to positive infinity. F of x goes to negative infinity. As x goes to negative infinity, f of x goes to positive infinity. And you might say, well, why do I need that? Well, we need to know where the function is going as it approaches infinity on the positive side and on the negative side. It's exactly what we had on the graph before. This graph that you saw here before. And this is going to allow us to graph the function on either end. Okay? So it's the end of the function is going to be one of these 4 cases. Okay? 1, 2, 3, or 4. One of these 4. The end of the graph has to be one of these 4. Okay? And the leading coefficient test by analyzing the end behavior will let us to do just that.